Hello, Dr. Armstrong here again. We are going to be starting the biomechanics unit. It starts with chapter 4, and I'll have more than one instructional video for this chapter, and we'll have a couple of different videos using some props to try to explain some of the concepts that I'd like to talk to you about. First of all, let me just remind you that this is part 2 of the course. We've looked at the introduction in terms of the skeleton and the muscular system. We're looking at biomechanics in part 2, and then part 3 is the muscles themselves. In this chapter, there are several PowerPoints that go along with it. We're going to be using material that we've learned in chapters 1 through 3 and applying them to the biomechanical principles in chapter 4. And hopefully we'll be able to retain this information after this section to apply to chapters 5 through 9. Let's begin with talking a little about motion. Relative motion. It's the motion of multiple objects or people in relation to other moving objects. For example, when you see one runner overtaking another runner, but they're both running toward the finish, they're both moving, but one is moving faster than the other. A person walking up and down the aisle of a moving bus. Another example, a long jumper taking off the board, and you'll notice I have 2 drawings here. The top one shows the actual jump through the air, and what I want you to notice is that we have 2 types of motion here. We have a motion of the jumper taking off and then his whole body moving with all its parts together in that parabolic arc. But then we also have the body rotating forward. Now in the bottom drawing, what I've done is give you the parabolic arc and then draw squares representing the body and then tilt them to some degree, showing that as the body moves through that arc, it will continue to rotate forward. Now hopefully you can see the problem with that, and we'll talk a little later, not in this video, but another time, about how a long jumper might compensate for that. We have linear or translatory motion, and this is again, this is an object that moves or translates as a whole from one position to another. We have angular or rotatory motion, and that's where an object acting as a radius moves about a fixed point. For example, levers or wheels, axles, and body segments, arms and legs. Now, it may be difficult to grasp because the full circles are not made in terms of when you're running and when the arms are moving, but this is considered to be angular motion. We have reciprocating movement, which is repetitive movement, like banging a hammer, bouncing a basketball up and down. We have oscillating movement, which is repetitive movement in an arc, as a pendulum moves. Levers in this particular chapter, we're going to be, it's important that you understand the basics of levers and be able to make the application of which lever to which type of movement, or the muscle is a particular class of lever. We're going to look at the 3 classes of levers briefly. Please make sure that you read that material in your book and you look at the PowerPoints as well. We have, like I said, 3 classes. First class lever has the fulcrum between the effort and the resistance. Now this would be like if you were to take a board and you were to try to pry a rock out of the ground. It could be a teeter-totter. A pair of scissors is an example of a first class lever. And a couple of things to remember about the first class lever. First of all, it has a mechanical advantage to it depending upon where the fulcrum is positioned. Now, can you imagine trying to pry up a board where the fulcrum was real close to the effort. Doesn't work. If you've ever been on a teeter-totter where the board is movable based on the weight of the individual, you can see where there's a mechanical advantage one way and not another. There are very few anatomical examples of the first class lever. The second class lever has the resistance between the effort and the fulcrum. Now it's a little different than what you may be used to. However, I want you to think in terms of a wheelbarrow, if you will. Think of a wheelbarrow. The wheel is at the end, that's the fulcrum. The load, the resistance, is in the middle, and your effort, the handles, is on the end, the other end. This type of lever always has a mechanical advantage. Doesn't matter where the fulcrum is placed, it doesn't matter where the resistance is placed, you're always going to have some type of mechanical advantage. There are very few anatomical examples of a second class lever. We mentioned that the wheelbarrow is a good example. A nut cracker, if you've ever used one of those to crack walnuts, that's a good example of a second class lever. Finally, the third class lever is what we deal with mostly in this particular class. And it's interesting to note that with the third class lever, the effort is between the resistance and the fulcrum. Now, if you look at this and think about, does this have any type of a mechanical advantage? It never does. However, just about every skeletal muscle is a third class lever. Now, I want you to think about that. Why would God give us muscles that are not mechanically advantageous? We'll talk about that a little later, but I want you to think about it. Like I said, it's never a mechanical advantage. Most skeletal muscles are third class. And what I'd like you to do at some point is look at pages 58 and 59 of the text very closely. What may look like first or second class muscles really end up being third class muscles. The key is where the distal attachment or the distal tendon attaches. If you look at the bicep and the rectus femoris, these are really good examples. A mechanical example, if you've ever opened a screen door with a spring that is attached at one end to the frame of the door, the other end just a few inches inside to the door, and it's kind of a lazy type of a lever. Over years it tends to stretch out. It doesn't pull the door closed very well. That's an example, a mechanical example of a third class lever. The fact is we don't have too many of them because they don't work that well. A little bit about speed and velocity. First of all, speed is the rate of motion of a body. How long does it take to get from point A to point B? For example, one lap around the Indy 500 course, which I think is 2.5 miles, you're not going the same velocity, the whole way around, yet you get an average speed. You use rate equals distance times time. You don't maintain the same speed all the way around. However, in terms of velocity, this is the rate of motion of a body, or the change in the speed. You have acceleration, which is increased velocity, and you have deceleration, or negative acceleration. I know that sounds like an oxymoron, but negative acceleration is decreased velocity. Here's an example. If you've ever seen the end of a 400-meter race, and you have 4 or 5 runners that are coming close to the finish line, and it seems like one is pulling away from the rest. Well, actually, at the end of a 400, all of the runners are decelerating. They're going slower. However, the one that seems to be pulling away is decelerating the least. speed and velocity. A little about acceleration due to gravity, or uniform acceleration due to gravity. All objects, regardless of their weight, fall with a consistent or constant acceleration of about 32 feet per second per second. 32 feet per second squared, or 9.8 meters per second per second. I'm sure you've heard the old joke, what weighs more, a pound of lead or a pound of gold? And in terms of, well, they both weigh the same. Well, how about if we drop them both, and if they weigh the same, even though one's bigger, one's smaller, one's more compact, what if we dropped a safe and a piano, or a penny and a piano? Which one lands first? Well, they both fall at the same rate because there's uniform acceleration due to gravity. Now you may be thinking, okay, but what about an arrow or a javelin? When you throw a javelin, especially the javelin that has been, in the last 10, 12 years has been redesigned, I've heard it say that you can throw the newer javelin tail first and it'll still land point first. So why does a javelin land point first? Or when you shoot an arrow, why does it travel in a long arc and then land tip first? It's not because the weight of the tip is heavier. Whether it is or isn't doesn't matter. It's because of the aerodynamic design. The arrow has the feathers at the one end, which cause it to the tip to drop. And then in terms of the javelin, it's the placement of the handhold as well as the shape of the tail. Now, it's true that all falling objects have uniform acceleration, but they are affected by the friction of air differently based on their mass and shape. For example, let's say I take a penny and an anvil, and I go to the top of the Empire State Building, I drop them both. Well, we know that they fall uniformly due to gravity, but going that far down, there is the air has a certain amount of friction and resistance to it. Well, the penny being lighter is going to be affected by the resistance of the air quicker than the anvil is. Therefore, it's going to slow the penny up. The anvil then actually would land first. A human body has what we call terminal velocity. In other words, when you drop when a person jumps out of an airplane and free falls, he or she can only go about 120 miles an hour. That is terminal velocity for a human being. That's for the same reason in terms of the amount of air friction and resistance. By the time the air resistance meets the resistance of the body, it stops the acceleration. It continues to drop, but it doesn't go any faster. Now you may remember a few years ago there was an individual who actually was released from some type of a plane or jet just into outer space, just above the atmosphere, and he actually reached speeds of in excess of 800 miles an hour on the way down. And you may say, okay, but what about terminal velocity? Well, the fact is there was no air. No air, no air resistance. Your next question might be, why didn't he burn up? Well, that's a good question. The fact is he wore kind of a heat shield type of outfit that prevented it. It's not unlike the heat shield on the space capsule. When it re-enters atmosphere, you're probably familiar with the fact that if it didn't have that heat shield on it, it would burn up as it enters the atmosphere. We also get into Newton's laws in this particular chapter. His three laws. The first one, the law of inertia. And this says that the body will maintain a state of rest or constant velocity unless it's acted upon by some external force. For example, a runner coming out of the blocks in a 100-meter dash, a drag racer from, you often hear they advertise a car saying it'll go 0 to 60 in 4.2 seconds. Well, from the very beginning, it has to have a lot more force just to overcome the inertia of standing still. A runner coming out of the blocks is standing still, therefore he or she needs more energy coming out. There's less force necessary going down the racetrack. So if you've ever driven a manual transmission car, and as you go faster, you have to shift up, and if you know anything about the transmission, you know that the gears are changing so that they are not turning as quickly as they were to give the car a lot more torque in the beginning. For a 100-meter runner, 50 meters down the track, he or she only has to kind of keep up with his or her inertia down the track, so less force is needed. The distance necessary to stop a car based on mass and velocity. For example, you probably were taught in driver's ed that you need to give yourself X number of car lengths so that you have room to stop. Maybe a better example might be as you think about a train, and a train, even going 20 miles an hour, I don't know how long it takes, but it takes a long time for a train to stop. It's because it has to overcome the inertia of moving. The law of acceleration. This says that the force applied to a body causes an acceleration of that body of a magnitude proportional to the force in the direction of the force and inversely proportional to the body's mass. So the formula that we use there is the force equals mass times acceleration. Now there are a number of really good examples in the PowerPoint, so make sure that you check that out. One of the principles that goes along with this law happens to be the conservation of momentum. For example, if you have a car going 20 and a car going 40 and they meet head on, well, the car going 40 is going to take it a little bit farther because it has more momentum, and that momentum has to be conserved. Let's say you are catching a baseball and they throw really hard, and how is that momentum conserved? Well, you might catch it and bring the mitt back so you don't get hurt, or you might just catch it and it just drills into the glove. If you've thrown a ball at all, you've probably been stung at times by a really hard throw. We see this principle in terms of a rule in football, in terms of taking care of the defenseless player. For example, a wide receiver who's up in the air, we protect that defenseless player, because if the receiver is up in the air or standing still, doesn't see the defender coming, he's coming in headlong, there has to be a conservation of momentum. So that person is not going to just stop that person, he's going to carry him on through. Finally, the law of reaction, and you know this as for every action there's an equal and opposite reaction. One of the best examples we have here that I've included in the text is rebounding. Now there was a player who you probably don't know unless you might be from Ohio. Jerry Lucas played back in the 50s and 60s and in the NBA in the 70s. Here's a bit of trivia for you. Jerry Lucas was the first player to win high school championship, collegiate championship, Olympic championship, and NBA championship. Now, there have been some others that have done it since, but he was the first. Well, the fact is that Jerry Lucas was one of the greatest rebounders ever. He played, like I said, in the 60s and early 70s in the NBA, and he still is among the leaders in rebounds per game. Why was he so good? And it wasn't because he was 6'9", but you know how big some of them are now. Well, the fact is that he claims that he memorized every player's shot in the NBA. He knew where that ball was going to carry him off of the backboard. He knew where the rebound was going, in other words. And here's another thing about Jerry Lucas that you may think, well, where have I heard that name before? It's not associated with basketball. Actually, he's a memory expert, and he does seminars all over the country in terms of teaching individuals how to memorize lists and so forth. There's another example that I give in the text, the continuum of running surfaces. It's on page 65 of the text. And what I've shown is a continuum is a straight line where we have a change throughout and it's going one direction or the other. Think of it in terms of I start off running in sand, and the sand, it gives, it doesn't allow me to get a good plant. Okay, then let's go from sand to dirt, dirt to grass, grass to hard dirt, then to maybe wood, pavement, concrete, stone. With each of those surfaces, as you run across it, the surface gives back. And if you've ever played basketball, for example, on a church basketball floor, a lot of them are asphalt, shingles, not shingles, but like linoleum over concrete, and there's no give to it, and you come away feeling really sore, as opposed to on a gym floor, which has a little bit of give. Okay? Center of gravity. It's been said that all sport movements are either an effort to disrupt equilibrium or gain equilibrium. Or when I say equilibrium, I mean balance. Or center of gravity would be, for example, in the body. Center of gravity is, you know where that is. It's about the middle of the body. It varies from males to females. But we tend to shift our center of gravity to help maintain or disrupt that equilibrium. We tend to use objects to help with the maintaining of balance. We manipulate our center of gravity, in other words. You would use this, for example, with in the application of lifting. And I have a drawing in the text of an individual doing a squat, and you can see how as you alter your center of gravity, it helps you with the actual lift itself. Finally, the last thing we'll look at tonight is stride length and stride frequency. How does a person run faster? There's only two ways. You increase your stride frequency or you increase your stride length. Stride length, the length of your stride, obviously. Stride frequency, the number of strides that you take, the quickness of your stride. How do you improve those? Well, you can practice stride length. There are drills that you can do where you can work to increase the stride length. If you have two runners with the same stride frequency, but one has a longer stride length, that runner will always win. At one of the, I think it was the 1984 Olympic Games, Carl Lewis was a four-event gold medalist, and he won the 100 meters. And they did a study where they counted the number of strides he took over 100 meters versus the rest in the final. And he took one or two fewer strides. Now that may not seem like a lot, but consider that we're only talking 100 meters, and the one or two fewer stride. A stride is probably between 7 and 9 feet. And so if he has the same stride frequency, you can see why he would have won. Take the case of Usain Bolt. Usain Bolt is 6'5", taller than Carl Lewis, and he probably has the longest stride of any world-class sprinter, which is why he has the world's record. Sometimes, if you're practicing stride length, trying to increase your stride length, you can go too far. and a stride length that is too far will tend to actually slow you down. Stride frequency, the speed of your strides. It's kind of difficult to practice. A lot of people think that you can do it by running downhill. It's true that if you run downhill, you tend to speed up your strides, but the fact is, and you'll note this drawing on page 68 of the text, that when you run downhill, you actually tend to increase your stride. You end up braking down the hill. You can actually increase your stride frequency in activities other than running. For example, riding a bike. It's obvious you can tend to increase that on a bike, a regular bike, a stationary bike, and so forth. Well, we are going to begin the next time with Bernoulli's principle, and please make sure you've read the text, and hopefully these videos are helping to some degree. These are some of the concepts and principles that I would be pointing out in class, and as always, if you have questions, please do not hesitate to email me or text me. Thank you very much, and I'll see you next time.